And both 11.9 and 11.10 are how to take functions and turn them into series. And the reason we want to do that is computers can handle series much nicer than they can handle functions. They can add up a whole bunch of terms. You tell it to just keep adding till the number doesn't change. That's a lot easier for a computer than to integrate a really messy inverse tan function or something like that. It doesn't have all that memorized in there. But it can change anything into a series, which is what we're going to do today. And we're going to start 11.9. It's on page 149 of your notes. We're going to start by remembering what we know about geometric. So when you have a generic geometric, notice I'm starting at 0 here. You can start at 1 if you wanted, but I'm going to start at 0. The first term is going to be plugging 0 in for n. So what's the very first term? A times r to the 0.
1.
1 times a. So it'll just be a, right? Because this part's 1, but this multiplied by the a. So it'll be a plus, what's the second term?
AR.
AR to the 1, right? And the third term would be AR squared. We're just plugging in 0, plugging in 1, plugging in 2. It's a kind of a little generic reminding you of what a geometric looks like. And we know the sum of any geometric is always equal to, that's in your notes there, a over 1 minus r. That's the sum of any geometric. If you know the first term and you know the common ratio, that's how you find what it adds up to. So we're going to use that for power series now, with x's in there. I lost my notes. There. So I want to let a equal 1. So the first term is going to be 1, and r is going to be x. A is 1, and the common ratio is going to be x. What will that look like? That will be 1 times x to the n. I put an a in for a 1 in for a and an x in for my r. So if I simplify that, that's just x to the n. What do we know that that adds up to? Using the same formula. What's a? 1 over 1 minus r, which in this case is x. So this statement right here is our reference for this entire section. What this statement tells us is you can give me a function, a rational function. If you want to graph this function, it's got an asymptote at x equals 1. It doesn't look anything like a polynomial if you go to graph it. But it's actually equal to an infinite series. This infinite series is actually the series of 1 plus x squared plus x cubed. All of that. If I add these forever like an infinite polynomial, it actually adds up to 1 over 1 minus x. So we can actually use what we know about geometric and take functions and turn them into series. That's the goal for today, to write functions as power series. There are some functions that are so messy there's no way to integrate them. For those of you who have to take Math 80 and differential equations, to solve a lot of these differential equations, you have to turn them into power series because you can integrate each term here. These are easy to integrate. That one, not so much. You need natural log, and sometimes it's so messy you don't even have any skills to integrate it. Okay. Oh, and then there's a note. We can only represent them as power series for a range of values, meaning you still need to know your interval of convergence. This might work if x equals 1/2, but it might not work if x equals 10. Right? Because what do we need to be true for geometric to make it converge? What kind of r will make a geometric converge? R less than 1. So the same thing would be true here. X has to be something less than 1, absolute value less than 1, to make it converge. Otherwise it would not be true. So let's jump right in, example 1. Example 1 says, find the power series representation for each of the following functions and determine its interval of convergence. Interval of convergence is what we just did on that quiz. So find the power series and interval of convergence. So I'm going to start with A. The function is 2x squared over 1 plus x cubed. So the goal is to take that function and turn it into a series, where all we know is that if it looks like this is how we turn it into a series. Well, this one has a 1 on the top. Mine doesn't. So I'm going to do some algebra manipulation to make that work. This is 2x squared times 1 over 1 plus x cubed. All right, I'm breaking this one up to try to make it look like this. First up, okay? What else is the issue? I have 1 up there now. What else do I need in the denominator?
Minus x.
I need a minus. So I need to turn this into a subtraction sign. So this is 2x squared times 1 over 1 minus what? Make it equivalent to that. Negative x cubed, right? Because minus a negative will give me that plus. So I'm just kind of algebraically manipulating the function that I have to try to get it in this form. Because in this form over here, my red, once I have an x right here, I know that that's what goes over here in my series. Well, in this case, I don't have an x, but this is what comes after the 1 minus in the denominator. So that's what's going to go over here in my series. This 2x squared, we're just going to let it hang out there for a moment, because it's kind of in the way. We're just going to hang it out here. But just this part over here, put parentheses around it, just this part is a series. N equals 0 to infinity of what raised to the n? If it's an x,
Negative x cubed to the n.
negative x cubed to the n. I have a negative x cubed here. So I have a negative x cubed to the n here. Whatever is coming after your subtraction right there is what gets raised to the n. Just like here, whatever comes after my subtraction is what gets raised to the n. It's following a format. This number in here, or expression, is the same as that expression there. If this had been a picture of a cat right here, I would have put a cat right there. Whatever's in there. So I have 2x squared times this series. Before I go on, is everyone all right with how I need to put the negative x cubed right there? Someone have to ask a question?
So it's just whatever the x term would be or is.
Yeah, whatever you're subtracting from 1. So whatever you have subtracted from 1, that gets raised to the n. That's our definition here. Whatever gets subtracted here gets raised to the n. So that's why you have to do that algebra manipulation to get a 1 on the top and to subtract something from 1. So from here, we just need to simplify. I'm going to do a little bit of simplifying here. I'm going to break this one up into the negative part and the part with the x's, just to try to separate those out. So the negative in there is really a negative 1 to the n. And then I have x to what power?
3n.
3n, right? Because we multiply exponents, so it's 3n. Now finally, I want to take this expression that I had factored out way back when, and I want to multiply it back in. I'm just going to distribute it back in to every single term. So what will happen? I will have a series that looks like what? Where's the 2 go? Kind of just goes out in front, doesn't really go with anything, doesn't have any powers, right? 2, -1 to the n. What happens with these x's?
X3n plus 2.
Yeah, 3n plus 2. We're just adding exponents, just like you would have any other time. If this was x squared and x to the 5th, you would have added them and made it x to the 7th. So if it's x squared and x to the 3n, we're adding those exponents. So this series is the same as this function, but only for some values of x. Before I go on, let me talk about what we just did. So the goal was to find the power series for a function. The first step was to algebraically mess around with it until we got the 1 over 1 minus something. It has to be in that form to be able to get the power series today. Thursday we'll have something else. From there, we use that same formula, simplify, simplify. Now we have a power series. So we've only done this part, finding the power series. Yes?
Can you explain how you got from like the right parentheses to the negative x?
Yes. So up here, we found that if it's 1 over 1 minus x,
Yeah.
that's the same as x to the n. So if I had 1 over 1 minus 1/2, that would have been the same as the series of 1/2 to the n. Whatever is subtracting down here is the same here.
Okay.
Agreed? So over here, instead of a nice number or just an x, we had this mess was being subtracted. So that mess gets raised to the n. Is that entered? You see it now? You're saying yeah, but I don't feel it.
No.
Okay. Other questions? So if this problem was on your web assignment, this is what you would write for your answer. Here's my series. Nice and simplified. You don't want to leave it simplified like this. This is not technically a series. This is an expression multiplied by a series, so you want to make sure you multiply that stuff back in. Okay, so that was the first part. We found the series. Now we need to find the interval of convergence. What am I going to do? Just erase what I was going to do. How do we find the interval of convergence? We use either the root test or the ratio test. Is this one an obvious root test one? Do I have powers of n everywhere?
Yeah.
That's not a power of n. That's a 3n plus 2. So multiplying it by 1 over n would not be nicer. It has to be just an n to do the ratio, the root test. So I'm going to use the ratio test instead. If this was an n, I'd agree with you. But if it's anything else, it won't work. So let's do the ratio test. We'll take the limit as n goes to infinity. Of the n plus first term. Again, I am ignoring the negatives because we're taking absolute values. So that is what happens when I plug n plus 1 in for my n. But I've just dropped this -1 because that alternating part will go away when I take absolute values. You can see what I did there? Put the n plus 1 in there. Divided by the nth term, which is 2 times x to the 3n plus 2. Right down.
Choose cancel.
Yeah, the 2's are going to reduce. That's nice. Those are gone. And then we're going to need to distribute this up here to see how many x's we actually have left. I can't quite tell. I see that some of them are going to reduce. So when we distribute that, that's 3n plus 3 plus another 2. So that's 3n plus 5. And this is 3n plus 2. there.
It's 3n. and the extra.
Yeah, I'm gonna be left with some 3n's. The 3n's are gonna reduce. How many more x's do I have up here than I do up here?
Three.
3 more, right? You take 3n plus 5 minus 3n plus 2, there's 3 extras. So this is just going to be x cubed. And I don't even need to take the limit as n goes to infinity because there's no n's in this expression at all. N won't affect this at all. So I need x cubed, that's my limit, and what do I need my limit to be? For it to be convergent, less than 1. So I need x cubed to be between -1 and 1. Which means that x has to be between cube root of -1, still -1, and cube root of 1 is 1. So that's the beginning part of my interval of convergence. I'm not done because I need to check the endpoints. Check the endpoints. So let's check x equals -1. And when I say check the endpoints, I'm plugging it in over here for my x value in my series. This is the series we're working with. So when I plug that in, 2 times -1 to the n times -1 to the 3n plus 2. I recopied this first part and then just put the -1 in there for my x. Simplify it. Don't assume it's alternating. It may or may not be. How many -1s do I have now? How many? None? Well, you're a step ahead of me maybe. I have n and another 3n plus 2 over here. So what do we do with exponents in this case? We add them. So that's 4n plus 2. Okay. N plus 3n plus 2. Now here's the key thing. You need to look at this exponent. What kind of number is that? It's even. It's always even. 4 times a number plus 2. Multiples of 4 are all even. Add 2 to that, it's still even. If you raise -1 to an even power, that's just 1. This right here is just 1. If it was odd, then we would have something that would be alternating, but it's not. It's even, so it's always going to be positive 1. N equals 0 to infinity of just 2.
So if it was +3, then there's a possibility it would be alternating?
It would actually always be negative. So if this was a +3, we would have 4n plus 3 as my exponent, right? So 4n is an even number. If you add 3 to an even number, it's always odd, right? Always odd, which is just equal to -1, because a -1 to any odd power will just be -1. So because of that 4n, it won't let it alternate. It makes it start off even and then it just shifts it to always be positive or always be negative. But you kind of have to inspect it. Everyone's a little bit different. So what about this series? What are we going to do with that? What do we want to know about it?
Diverges or not?
Yeah, we want to know if it diverges or converges.
No, you diverge.
Divergence test for sure. The divergence test says that if the limit of your general term is not equal to 0, then it diverges. Those terms have to approach 0 to have any hope of converging. So -1 is not included in my endpoints. Now let's check positive one. Two times -1 to the n times +1 to the 3n plus 2. here.
Just,
What'd you say?
you just add them,
Well, I can't add the exponents, these are different bases. Go ahead, say it.
It's always one.
It's always one. One to any power is just one. So this is just one. I don't care what that exponent is. 1 times however many times is still 1. But we can't combine those because they were different bases. Up here, they were both -1, so of course it made sense to combine them. So this is the series, n equals 0 to infinity, -1 to the n times 2. Oops, I put the 2 on the back. Same thing. What kind of series is this? This one's alternating now, because I still have this alternating part in there. So I'm going to use the AST. Limit as n goes to infinity of 2 is equal to 2, and that's not 0. That one diverges 2. So my interval of convergence is -1 to 1. Oops, 1. That's a round one. Seems like a lot of work to not use your endpoints, but some endpoints work. And you maybe could leave the -1 in there or the +1 in there, so you have to check. This happened in my first 2 examples, they both did not have the endpoints included. A lot going on in that one problem. A lot going on in that one problem. Questions? So notice this problem. The first half of it is really 11.9. The second half of it is a little 11.8 review. 11.8 is a long section. Each problem a little bit messy. Let's try another one. I'm going to leave this formula over here. And I'm going to start with B. This is the same example 1B, where I have h of x is equal to x over 5 minus x. Same directions. Find the power series and the interval of convergence. So what do I want to do to turn it into a power series?
Pull the x out of the numerator.
Pull the x out for sure, because he's recognizing we want to have that 1 on the top, so that's great. So we'll pull the x out of the numerator, and I'll have 1 over 5 minus x. So that's good, we matched that guy up. Now what's the issue? That 5. This is not supposed to be a 5. It's supposed to be a 1. What'd you say?
So when you have the, like.
Never mind.
Multiply by both sides by 5.
So we're not multiplying by 5, but we're actually going to factor out the 5. And if I factor out the 5, then it'll be a 1. And some of you are going, but wait, I can't factor out the 5. I claim you can.
You do x over 5.
5 times 1 minus, what'd you say, Joseph? X over 5, right? We can pull out the 5. Yeah, it gives us fractions, but we can pull out the 5 and force it to be a 1 right there. Algebra, it's our friend. So I'm going to take this 5 that we pulled out and move it all the way over here with this x, just so it looks prettier. So the 5 that came out is going to go over here, and now I have this. So we did the algebra manipulation to get it to the point where this portion now is in this form. Okay, this one looks like that one. And the part that goes in my little red circle is just this part. That's the part that's being subtracted from 1. So that's the part that will get raised to the n in my series. So that means I have my x over 5 in the front, because he doesn't follow the rules, so he's just out here waiting patiently. But the rest of it becomes n equals 0 to infinity of what?
X over 5 to the end.
The whole quantity x over 5 to the n. Okay there? Now we take this x over 5 and put it back in. So what do we end up with?
I put X over 5 to the 2n.
Say that again, I couldn't hear you.
Is that I put X over 5 to the 2n?
Ooh, you're close. There's an n here. What's the exponent on this over here though? It's just 1. Right, there's only one of them out there.
Let's see.
So I don't have an n plus an n.
Plus one.
N plus 1. Because whatever number you have here, see that, Joseph, there's just one more?
Yeah.
2n would have been if I had another x to the 5 to the n over here. So this is my power series. This is the series that for some values of x is the same as this function. Before I finish that, I guess I didn't follow up with what this tells us. When we found our interval over here between -1 and 1, this tells me that if you pick any x value in that range, you plug it into this function, it's the same as plugging into this series. You could add a bunch of terms and get the same answer as if you plug it into the function. And eventually, the terms get so small that you could ignore them. So maybe we only have to add up the first 700 terms to get a pretty good approximation, but a computer can do 700 terms in the blink of an eye. Questions up to that? Now what? Now what?
Ratio test
Ratio test on what?
on the new series, the DX.
Okay, so I like where you're going, but why are we doing the ratio test?
Because we need to find the actual one.
Aha, we want to find the interval of convergence, so that's, so make sure I know. We're not checking to see if it converges, but we're looking for the interval of convergence. So this is where we either do the ratio test or the root test. So let's do the ratio test. This looks very familiar, we'll bring it over here. Fair warning, I think these end-on don't work either, but we need to talk about it. Okay, so we'll do the ratio test on that new series. Again, ignoring the alternating part. You said, oh, there's no alternating part, never mind. So I have x over 5 to the n plus 1 plus 1. Right, plugging in n plus 1 into there. Divided by, but instead of dividing, I'm going to flip it over and multiply just to save space. Divided by x over 5, which is now 5 over x, raised to the n.
Plus one.
Did it have a plus 1? Oh, you have a plus 1, thank you, plus 1. So that second term is just flipping this one over and multiplying instead of dividing. Right? Dividing by x over 5, the same as multiplying by 5 over x. What happens here? How many x's do I have on the numerator? X to the n plus 2. And in the numerator, I have 5 to the n plus 1. And the denominator, I have n plus 2 5s. And n plus 1 x's. Just kind of breaking those both up in the numerator and denominator so we can see it better. What's going to reduce?
You're gonna have one more 5 in the denominator.
One more 5 in the denominator, right? Because I've got n plus 1, I got 1 extra. So these are gone, I just have a 5 down here.
Or you're gonna have one more x in the numerator.
And 1 more x in the numerator for the same reason. I'm just subtracting the exponents. And again, the n's are completely gone, so I'm just left with x over 5. And to force this to be convergent, I want that to be what? Less than 1. Now, I just want to talk about something that's going to come up in later problems. Remember we talked about the interval of convergence and the radius of convergence? So for example, here, the radius of convergence was 1 because from the center you can go out 1 in either direction. The radius of convergence you can often find without finding the whole interval. Problems coming up later on, just ask for the radius. So I'm going to find the radius first and then I'll find the interval. To find the radius, just isolate the part with the x. I'm going to multiply both sides by 5 right here. Agree it's the same statement, multiplying both sides by 5. This tells me that my radius is 5. I'm allowed to go 5 away from x. Right, that's what that tells me. So I know the radius is 5. And then my interval becomes negative 5 to 5. A lot of problems in this section, because it's so time consuming to find the whole interval, just ask you to find that radius. And by isolating that portion, you can find the radius. Am I done? You guys all wish I was, I know that. Is that my interval?
Check the endpoints.
We need to check the endpoints. We'll go through that part kind of quickly because you guys get tired of it anyhow. So I have to check x equals negative 5 and x equals 5 and see if either one of those works. I think I have yet again picked one where neither of the endpoints works, which is hard to point out why it's so important if I don't pick one where they do. But I think neither one works again. Well, let's find out. So where am I checking them?
Negative 5 and 5?
Yeah, but what do I do with those?
Oh, so it goes back into the original.
It's the original
Series.
series over here. I need to plug them in over here. So when I check negative 5, that's negative 5 over 5 to the n plus 1. Which simplifies to what? It's an alternating series. Negative 1 to the n plus 1. What's the non-alternating part of this? This is the part that makes it alternate. Yeah, there's an invisible times 1 right here, right? That's the bn, they call it, the part that's not alternating. So we're going to have negative 1, positive 1, negative 1, positive 1. Well, this one's alternating, so we can use the AST. Find out what that limit is. The limit of 1 is 1, and that's not 0. So it diverges at x equals negative 5 using the AST. By the way, if you tell me you're using the AST before you start, you don't have to tell me again at the end that it diverges by the AST. I can see that's what you did. And then if we check positive 5, that's the sum of 1 to the n plus 1, reducing those 5s, which is just 1. So this is the series where we're adding 1 forever. Give you $1 every day forever. Even after you're gone, we just keep adding $1. What can you tell me about this series? Diverges because divergence test. So the divergence test, the limit as n goes to infinity of 1 is 1, and it's not equal to 0. So it diverges. So that tells me my interval is -5 to 5. So that tells me that if you pick any number in that range, and you plug it into this formula here, your answer, if you could add an infinite number, is almost identical to plugging it into the original function. Let me give you a for example. Let's show you for x equals 0.1. Just pick the number in this range. The function h of 0.1, where's my function? X over 5 minus x? 0.1 over 5 minus 0.1. See what I'm doing? I'm plugging it into the actual function so you see what we're getting. 0.1 over 4.9. Can somebody punch that in their calculator for me? I can't do that in my head. What did we get there? Some small number. 0.0 something.
0.0204.
Thank you. And it keeps going right after that. So what we just found is that if we happen to choose that x, we can do this series. Is it x over 5? Of 0.1 over 5 raised to the n plus 1. And we should get about the same answer. But we're not going to add an infinite number of terms because you guys are all about ready for a break anyhow. That's too long to add all these terms. But we're going to start writing out a couple terms to get the idea. For the first term, I'm going to plug 0 in here. So I get 0.1 over 5 to the 1 for the first term, because 0 plus 1, plus 0.1 over 5 squared, when I plug 1 in there, plus 0.1 over 5 cubed, plus, and I gotta keep going, right? Everyone see what I'm doing there? Somebody do me a favor, just add these first 3 terms up. Just the first 3. See what we get. Okay.
So wouldn't it be 0.111 over 5?
Well, this is 0.1 over 5, and this is
Oh,
the
added.
0.1 over 5, the quantity squared added to that one,
Gotcha.
right? So I want to know what those 3 things added up equal. Anybody get it?
I got 0.0204.
Huh, what a coincidence. When you add these 3 terms, it already matches the exact value of this function up to 4 decimal places, just by adding 3 terms. It might even match for more decimal places. We didn't write any more down. If we, what you got after? We got a couple more?
Matches to 6 on mine.
Does it, so tell me what you got?
0.8.
0.8?
Yep.
And this one was a 0.8 also?
Yeah, and that one kept going to the top.
And then this one changes and this one stops right here because we only added 3 terms. But the point is, to 6 decimal places, all you have to do is add 3 terms versus find the actual value of this function. So, you know, I always like to joke about, if I'm stranded on a desert island, I have to do some calculus and I don't know how to integrate, I can't do all this fancy stuff. If I can't evaluate a function, I can always just add a bunch of numbers, especially if I'm stuck on a desert island with nothing better to do. I can add for days on end. But this is actually how calculators and computers actually evaluate integrals and derivatives and evaluating certain functions. The function itself is too messy for it, but what it does is just adds enough terms until that the change is so small that they're like, okay, we can stop here. Maybe up to 8 decimal places we're good, and we don't need to add any more. In this case, you only had to add 3 terms. it turns out that the further you get from the center here, the more terms you need to be more precise. So like if I went all the way out to like 4.9, I probably would have to add a few more terms to get more accurate answers because it's on the edges of my interval, but it would still work. Okay, let's go ahead and take a break. Because here's the good news, it gets harder after this. Just so you know, in case you didn't already know that. We'll take a break, we'll come back in 10 minutes, and then we'll do some more with changing functions into series. Where we left off and see if we can handle this messy notation. So I'm now on page 150. Page 150, and we're going to start taking derivatives and integrals of these functions. Because life hasn't been complicated enough already. Which means we're taking derivatives and integrals of these series. So at the top of this page I have a lot of this written out, but it kind of helps, I think, to talk through what it all means so it doesn't look so overwhelming. So the theorem says, okay, imagine that we have just some generic power series centered at A. So that who knows what the constants are, they might all be different, the constants in front. Each term has its own constant, x minus a raised to some power. That just means you start with C0, and you don't have any x minus a's in that first term. Then you have C1, x minus a to the 1, C2, x minus a squared, and I even added a third one up here, C cubed, x minus a to the third. That's the generic notation for a power series. So what I want to do is take the derivative of these terms. We'll worry about what comes over here. Well, let's just take derivatives knowing what we know. What's the derivative of a constant? 0. Plus, what's the derivative of this?
X minus
It's C1, but what's the derivative of x minus a?
We're taking her to dx.
We're taking the derivative with respect to x. X is our variable.
So you're gonna have 1 plus a times dA, or a prime.
If this is my y and I want to take the derivative of this, the question is, what is the derivative of that? You bring down the 1, right? And then it's x minus a to the 0. It's just 1. Derivative of x is 1 and derivative of a is 0. So this derivative is c1 times 1. What about the derivative here? What do I need to do?
2.
It's going to have a c2 in it, but then what do I do with the 2 up there?
Chain rule.
Chain rule, right? So bring down the 2. So that'll be 2c2 x minus a to the 1, right? Derivative, we just bring down the exponent and subtract 1. That hasn't changed. It just looks scarier when you do it here. And if we do it one more time, what's the derivative of this guy?
3c3
3c3 x minus a
squared.
squared, and then that would keep going forever. So in general, for every single term, what I did is easier to see over here. You bring down the exponent, and you subtract 1 from the exponent, just like you've always done. So that's where this notation comes from over here. It looks like this, and I want to point something out here in a second. X equals 1 to infinity, n times cn times x minus a to the n minus 1. So here's where the exponent came down in front, right? The n came down in front, and then we subtracted 1 from the exponent, just what we were doing on the other terms. What else do you see different between here and here?
The n.
Yeah, the n starts at 1 down here. Start at 0 up there. Why does it start at 1? And not at 0?
0 goes to 0.
Yeah, that C0 went to 0 right here. This guy's gone, right? He's not here. So this is my first term now. I'm starting with C1. There is no C0 term anymore. So this started with C0. This one starts with C1. So they actually have to adjust this a little bit when you take derivatives. Similarly, you could integrate this function. Take the integral of f of x. That's my next line on there. I'm not gonna write out each term, but it's the same idea. The integral, blue pen, if it worked, I'm gonna switch it again. If I integrate this term, when you integrate, what do you do with the exponent? Like if I wanted to integrate this term, what would you do with the exponent?
Divide by it.
Add 1 to it, so it'd be a 4, and then I would divide by it? So we'd add 1 and then divide by that new exponent? That's exactly what I have written there. If you look at my notes, we'll talk about the rest of it. I'm going to switch pens. This one's speaking, not blinking. I'm running out of my blues. Let's see if we like this one. I'm still starting at 0, because even that term I could integrate, right? I could add 1 to my exponent. So I take my Cn, I have my x minus a raised to 1 more, divided by that. Did I write it in the same format? Close enough. The Cn I have off in the front on my notes, but I could put it in the numerator as well. Yeah, my notes, it actually looks like this. Like the Cn down in front, it's the same thing though. See that in the line number 2? And then because we integrated, there's a plus c at the end, but there's an infinite number of terms here, so they put that plus c in the front. That's the same as if you wanted to integrate each one of those separately, which I'm not going to write out right now. I think you'll be able to follow it. The whole point is that when you have functions that are written in a series, you can take derivatives and integrals. They will have the same intervals of convergence and the same radius of convergence. And the reason we care about that is not every function can be put into this form, which I moved over here during the break because we're going to still need it. Not every function can be put into this form, but maybe it can if you use integrals and derivatives, which is what my next example is going to do. Okay, so let's jump in there. Example 2a. Example 2, by the way, says find the power series and just the radius of convergence, not the whole interval, so it saves us a little bit of time. So I have g of x equals 1 over 1 minus x, the quantity squared. So that does not look like the formula that's way over there on the left. And there's no amount of algebraic manipulation I can do to make it look like that. I mean, it looks like there's the 1 minus x squared. The squared's the problem, right? We can't have a squared there. But what's the integral of this function? Just a little review problem for you. What if I want to integrate this function? I'll rewrite it one other way so you can see it better. The integral of that function. Could you integrate it? What would you do to integrate it?
Add 1 to the power.
Add 1 to this exponent. So that'd be 1 minus x to the negative 1. And then I would divide by that negative 1. But there's also a little mental use of, or reverse chain rule. You have to also divide by the derivative of the inside, which in this case is
-1.
another negative 1. So there's actually another negative 1 out here. So that's just positive 1 over 1 minus x. The integral of our function, this is our function, g of x. The integral is this one. I'm going to call it f of x. I'm going to call it capital G, actually. That's better. That's what we used to call it way back when we first learned antiderivatives. Do you agree that that function is the integral of my original function? before I do anything with that. It's supposed to be a box. That's left. What happens if I take the derivative of this function? What happens if this function is the integral of that function? What's the derivative of this one? It's just g of x, he says. Right, that's what it means to be the integral, that when you take the derivative, you'll get back to the other function. Integrate a function, then take the derivative, you'll get back to where you started. We're gonna need that in a minute. So we took our original function, we integrated and found g. This is g of x. Can you write g of x as a power series? Hopefully we can, quickly and easily for that one. What is g of x as a power series? It's just x to the n. That one matches our formula exactly, right? It matches our formula over there. So that means this is the series n equals 0 to infinity of x to the n. So I took our original problem, I integrated it. The reason I integrated it was because I needed to get rid of that exponent of 2 in the denominator. I needed it to be an x to the 1. So the only way I could change it is to integrate it and make it go up by 1, from a -2 to a -1. So I integrated it and got to here. Then I wrote that one as a series, using our same formula we've been using. But this is capital G of x. This is why I had this conversation over here. If that's capital G of x, how do I get back to G of x? Little g? Take the derivative, right? So little g of x, the original function, is the derivative of this guy, which is the derivative of this guy, what's the derivative of that guy?
N times x to the
N times x to the n minus 1. Just using your derivative rules, right? Bring the exponent down and subtract 1. Now, I wrote it starting at 0. It's not wrong. It's not wrong, but it's unnecessary. What happens when I plug 0 in here?
It goes to 0.
I get 0 anyhow. The first term would be 0. So most of the time you'll see it written, every time you take derivatives this will happen. We'll start at 1 instead, because the 0th term is 0 and it doesn't do us any good. So just start with 1 and go from there. So this guy, they're both equivalent, but this is the one that's more common. You'll want to watch that when you're doing them on WebAssign, for example. They'll put the beginning part of the series in there for you. You want to check to see if they're starting at 0 or starting at 1, because sometimes it will affect a little bit of what you're going to write. But technically, in this problem, they're the same, because when you plug 0 in, it's just 0. But this is the power series for this function. And the only way we could do it was by integrating and then differentiating to get back. N equals 1 to infinity. And x to the n minus 1. It might not be obvious either that you need to take an integral first to get started. Sometimes you integrate, sometimes you differentiate. You're just trying to find something that looks like 1 over 1 minus x. So in this case, because I had the extra exponent in the denominator, I knew I needed that to go down by 1. So I had to integrate. Questions there? Kind of weird. Yeah, Joseph.
No, what's the difference between the capital G of x and the lowercase g of x?
Say that again, I couldn't hear you.
The difference in the capital G
Ah.
of x and lowercase g.
So the lower g of x was the original function. Capital G is the integral of that.
Okay.
So it's this function right here. So if I line them up, capital G of x turned out to be 1 over 1 minus x.
I just wanted to make sure like that's why it was capital, not.
Yeah, that's why I chose capital G. So this was my original function. I took the integral, worked backwards, and got this function, called it capital G. And the derivative of capital G is little g. Yes,
Why couldn't you factor out a 1 minus x?
I could have written it like this. But these are both power series. So if you tried to write that out, this is this series, and this is this series. And to multiply these back together, you would have to do FOIL with an infinite number of terms, which is virtually impossible to do. Right, this is 1 plus x squared plus x cubed, goes on forever, times another one of those. See the problem? We're gonna run out of terms pretty soon. We're gonna be real tired of multiplying those out. Because I got 1 times all these plus x, and there's just infinite. So you can't really multiply two series together. There's no way to do that, because it's an infinite number of multiplications. If it had just been a constant or just one term like we saw earlier, that's one thing, but when you have a whole nother series, it's a mess. Good question, though. Okay, so the second part was to find the radius of convergence. That's what I was warning you about before. You don't have to find the whole interval, just the radius. So all you have to do is just the root test or the ratio test just to find the radius. So for this particular series, which test do you want to do? The root or the ratio? The ratio too. There's not nice powers of n. So if I do the ratio test, we can find the radius of convergence. So I'm going to take the limit as n goes to infinity of the n plus first term over the nth term. I plugged in n plus 1 for all my n's, plugged in n for all my n's. What reduces here?
X n minus 1.
Yeah, the xn and the xn minus 1. I have one extra x up here than I do down here. N goes to infinity of n plus 1 just times x, and then n down here. Because one extra x on the top. That was the first one today we've seen like this. We've seen them before, but there's still n's in here. But remember, the x is not affected by the n's at all. So I'm going to factor that out. Pull out the absolute value of x and just multiply that by the limit of this part. What does that limit go to? That just goes to 1, right? N over n, 1 over 1. So this equals x, absolute value of x, excuse me. And I want that to be less than 1 to make it converge. And I already have the x portion right here isolated, so that tells me that my radius of convergence is 1. If it had ended up to be this, x less than 7, then the radius would have been 7. This is I'm allowed to go 1 away from the middle. So that part's a lot easier than finding the whole interval. Checking endpoints, it would take forever. Okay there? Okay, look at B. Look at B. Same direction. Natural log of 1 plus x. I want to turn it into a power series. The only way I know how to turn it into a power series is to make it look something like this. Yeah, let's take the derivative, because we take the derivative of a natural log. That's gonna be 1 over 1 plus x. Derivative of any natural log function. Now it looks a lot like this, except for,
X is a positive solution.
yeah, I've got a plus instead of a minus. But we know how to fix that. That's 1 minus a negative x. Agreed? Can we write this as a series? That's the sum, n equals 0 to infinity of negative x to the n. Right, replacing my negative x in that formula, just like we were doing earlier, when we thought those were hard. Now this is my derivative. I want to get back to the original function. If this is the derivative of my function, what do I need to do to get back to it? I have to integrate it. I took the derivative, now I need to integrate it. So let me move this up top so you guys can see it back there. So the derivative, I'm going to simplify it by breaking out the constant terms and the x terms, because it's going to be affected by the derivative. Do you agree that this is the same as negative 1 to the n, x to the n? That's f prime. So if I want to go to f of x, because this is the derivative, to get back to my original function, I need to integrate this. Lots of variables, but remember x is our only variable. So how do I integrate x to the n? What do I do to the exponent? Add 1 to it. What's this negative 1 to the n out front?
No, it's a constant.
It's a constant when you're integrating because it doesn't have any x's in there, so that's really a constant. So I'm going to have the series n equals 0 to infinity of negative 1 to the n, that's just a constant, times the integral of this, which is x to the n plus 1 over n plus 1. Plus some c, because I integrated. There's some other constant out front there. A lot of times they'll put that c in the front, c plus, but it doesn't really matter. But that c is not part of this term. There's the series plus the c, which is why they often will write that in front, so there's no confusion. Okay there? And then we need to find out what that c is using the original function. So we now have the function here. If this function equals that series, when I plug any x in here, I should get the same answer that I do over here. Tell me an x to plug in here that would make the answer come out really nice.
0.
0. If x equals 0, what's the natural log of 1? 0. So we know that f of 0 equals 0. Just by plugging 0 into this function. What should happen when I plug 0 in over here? If they're equal, if I plug 0 in here, it should equal 0. F of 0 should be c plus this whole series here with a 0 in there. What does that tell me every term equals? 0, right? Every term's going to be 0. 0 plus 0 plus 0 plus 0. So what does c have to be then? if this part all adds up to 0, we know this part all adds up to 0. C better be 0. This tells me that C better equal 0, otherwise this won't be true. There are other functions where C turns out to be the square root of 3. But in this case, C equals 0, which means that for our final answer, we don't need this part. I'm actually going to leave it up there, right. So my original function, which was the natural log of 1 plus x, is equal to the series n equals 0 to infinity, negative 1, x to the n plus 1 over n plus 1. That's my power series. Questions then? Yes?
So were you saying that when we do integrate, we have to find out if C is some value other than 0, and we'd have to include that in our?
Yes, exactly. So I can't come up with one off the top of my head right now. But let's say you had some function, I don't know, natural log of x plus 4 or something like that, right? I would maybe plug x equals negative 3 into here, because negative 3 plus 4 would give me natural log of 1, which I know the answer is 0. So in that case, f of negative 3 would be 0. So I would then have to plug like negative 3 into here to figure out what happens to see what that constant would be. See what I'm saying? And it doesn't always have to be the same. You can plug in anything you want. The problem is some numbers make it messier and harder to solve, and some make it come out nicely with a bunch of zeros. I hear wolves next door. Do you guys hear them? There's wolves next door. Just making sure I'm not hearing things. Okay, we also would need to find the radius of convergence for this one. In the interest of time, I'm not going to find it. What would I do to find the radius of convergence?
Ratio or root test?
Yeah, ratio or root test. Convergence, if I could spell. This one turns out to be 1. Again, it's almost identical to the last one, which is why I'm skipping it. Ratio test would be best in this case because I don't have nice powers of it. It's almost identical to that last one. So the radius would be 1. I want to do a slightly different problem here. Okay, I'm skipping that part. Okay. Let's look at C. Let's look at C. That's a pretty one. Inverse tan of x. This is how computers and calculators actually evaluate inverse tan of x. They change them into series. Inverse tan of x, same directions. We want to turn it into a power series, find the radius of convergence. Anybody know anything about the inverse tan? Oh, we know the derivative of it, which I've only asked you to memorize like 100 times so far this semester. 1 over 1 plus x squared. My H looks really weird right here. So Chad remembers the derivative and he had a little question mark in it, but he was right. That's the derivative of inverse tan. Remember back in chapter 7 you had to recognize it because we were integrating it everywhere? That never goes away, that inverse tan. So if that's the derivative of it, that's helpful because this derivative looks a lot like the formula that we're trying to match up to. What do I need to do to it? Turn into a power series by doing what with this? I didn't make that negative. I'm going to have to take an integral when I'm done. So hang on, we're doing a couple different things. First off, to turn this into a power series, I need this to be a minus here. But once I do get the power series, Zach's totally right. I need to take an integral to get back to the original one. But I gotta get the power series first. So if I integrate it now, I know the answer is inverse tan. Oops, 1 minus negative x squared. Good? So now we can turn it into a power series of
And put negative x squared to the n power.
beautiful. Negative x squared gets raised to the n power. Whatever we're subtracting from that 1 gets raised to the n power. And because we have to integrate, I'm going to again separate the constant terms and the x terms, or the constant factors and the x factors. So I have a negative 1 to the n, that's the negative part. What happens here? X to the 2n. We multiply exponents in this case. So that's my power series for the derivative of h. That's the derivative of h. So to get back to h, what do I need to do?
You use integrate
I have to integrate. So since I took the derivative, I now have to integrate to get back to where I started. So h of x is going to be the integral of this series with respect to x. When you're integrated with respect to x, this negative 1 to the n is just a constant, doesn't change with x. So that's good. So that's going to be, I'll write the integral sign again. The negative 1 to the n I keep. Be careful here. What do I do to this x to the 2n?
2n plus 1,
I add 1 to that, so it'll be 2n plus 1,
all over 2n plus 1,
all divided by 2n plus 1,
plus
plus some other c over here. What is h of 0? I almost always am going to plug in the center of this because that makes every term go to 0. Right? H of 0, what's the inverse tan of 0? What angle has a tangent of 0? What angle has a tangent of 0? There's trig again. We thought we got past all those chapters with trig.
Pi over 2.
Pi over 2 is a tangent that's undefined. Pi has a tangent of 0, but the inverse function is only defined from 0 to pi not including pi.
So 0.
Or negative pi over 2 to pi over 2, so it has to be 0. You're right, that pi does. There's an infinite number of answers, but we need to make sure when you're doing inverse trig functions, there's limitations on your range to make sure it's actually a function. But the tangent of 0 is 0, so the inverse tan of 0 is also 0. If I plug 0 into all of these, I'll get 0.
C is the
So C has to be 0 again. So C equals 0 again. Which means that h of x, which is the inverse tan of x, is equal to the sum of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1, and we don't need the c. There are times when c is not 0 though. You'll see some of those on your website. The trickiest part for these, I think, is recognizing when to take derivatives and integrals to see if they're going to get you anywhere. Questions? Think we got it? Let's do the radius of convergence for this one. I think it might be different. I don't know, I haven't found it. Did I find it? No, I didn't. It's from -1 to 1 again. Darn it. Sorry. -1 to 1. So that one, I don't want to find the radius of again. It got to be the same formula again. Been a little boring. We saw some other ones. I was going to say one more thing, but it's got lost track. I looked that up. I forgot what it was. So then we'd have to still find the radius using the ratio test again. Oh yeah, it would be 1. Ratio test again. This one though, that's what I was going to say. If you found the endpoints, the actual interval, endpoints work in this one. But we're just going to do one last problem and we should be good. Okay, we can handle this. Example 2. Do you have endpoints on your integral there? You should. Mine shows that we made a correction, but I don't know if we made it onto yours. You should have the integral from 0 to 0.5. You guys have that on there? Okay, add those on there, please. 1 over 1 plus x to the 7 dx. And the directions say to evaluate this as a power series. And let me tell you why. There is no nice way to integrate this. I don't know how I would integrate it if you told me to do it using calculus. Maybe I would try integration by parts. It's not really partial fractions because there's just the 1 on the top already. There's like not much I can do. I don't know what I could do to actually integrate that and plug those values in. It looks nice and simple. So there's no, you can't do a U sub. There might be some weird technique that if I spent a few hours I can come up with it. But instead what I'm going to do is just turn it into a series and integrate the terms because I can integrate each term. So I'm going to turn it into a series first. What am I going to do with this function?
You have to make it x be negative x.
I have to make it 1 minus a negative x to the 7. So when I go to write it as a series, it will be negative x to the 7th to the end. And then if I simplify that, that's negative 1 to the n, x to the 7n. So that's just rewriting my function as a series. We're okay with that? So now I'm going to do this. I'm going to plug it in here. I'm going to evaluate this integral. And instead of 1 over 1 plus x to the 7, I'm going to write this. Oops, I lost my series notation. Hang on. I'll move it over. I'm going to integrate this guy instead. He's the same function, just in disguise. So when I integrate it, I'm still going to have a series. This is a constant. Oops, my n fell off. Negative 1 to the n is still a constant. What do I get when I integrate this term? X to the 7n plus 1? All over 7n plus 1? Technically there's a plus c, but because I have a definite integral, I don't need the plus c. And then I have to evaluate this from 0 to 0.5. So I'm gonna plug in 0.5 for x. N equals 0 to infinity, -1 to the n, 0.5 to the 7n plus 1 over 7n plus 1 minus. Now I'm gonna plug 0 in there, and some of you already see it, but I wanna write it out so everyone sees what it does. So I plugged in 0.5 for x, and I plugged in 0 for x. I'm gonna make it just bear that. What happens to this series over here?
Is zero.
It's just 0. Every term is equal to 0. So this guy's just 0. So this integral is equal to this series. So what it means to evaluate it, usually I don't have the directions on there, do I? We evaluate it and we want it correct to a certain number of decimal points, maybe to 3 decimal points or to 4 decimal points. It's like that example I showed you before. So this is equal to, now we're going to write out each term. If we start with 0, -1 to the 0, that's +1. I'll have 0.5 to the 1 over 1. So my first term is 0.5 to the 1 over 1 when I plug in 0. Minus, now I'm plugging in a 1, that's why it's minus, -1 to the 1. 0.5 to the 8 over 8, because I plugged 1 in there. Let's do one more term. If I plug 2 in there, that's squared, so it's positive. 0.5 to the 15 over 15, and it keeps going. See what I'm doing there? Can someone just tell me what this term is equal to? Just this term right here?
It's 2.035 times 10 to the -6.
-6, you said?
Yeah.
Oh, sorry, I put too many zeros. -6, 1, 2, 3, 4, 5, okay. That's what just this term is. So, it's to 6 decimal places, it's pretty damn small. You go another term, it's gonna be okay, like 0's out to 8 decimal places. Eventually, these terms are so small that we don't care anymore. So if we just add these 3 terms, that's a really good approximation for the whole thing. Yes, there's an infinite number, but the next term after this is gonna have like, I don't know, this was 6 zeros, it's gonna have like 13 zeros. It's rounding to 10 decimal places or something. We don't need more than 3 decimals. So we would just need to add these 3 terms to get an approximation for what the whole thing equals. I don't know if I wrote this down already. I think I did. Looks like I have 0.499502. If you take this one minus that one plus that one. So even though this is technically an infinite series, once you decide your accuracy, you don't need that many terms of it. We only needed 3 terms to get accurate out to 13 decimal places. Yes?
When I do it on my calculator, I get like, it's not even rounding, it's just 0.5004.
This one?
Or for when I add up the 3.
Oh, did I maybe add wrong?
Yeah, I'm getting 5, or
Oh, maybe I did a mistake.
5005.
Okay. Double check. Did you remember to subtract this one?
Oh, no, I have.
Well, it's got to be less than 0.5 because we're subtracting. Double check with the minus. Tell me again before we go, make sure, in case I made a mistake.
That's right.
Do you agree with mine?
Yeah,
Jose and I agree. You're overruled.
it's good now.
And the minus sign makes a difference. So this is actually how computers and calculators do all kinds of real-life applications, any kind of engineering applications. They don't know how to evaluate some of these messy integrals, but they punch it in there, they turn it into a series, crunch out enough terms until the terms are, what you're adding is so small it doesn't matter anymore and it stops. Okay, I've narrowed in on my answer. This is why we care about this whole series section. Okay, I will see you on Thursday. Don't forget you've got 2 sections due on Thursday. The one about finding intervals and radius and radii, and then turning things in the power series. And Thursdays are